Okay, welcome to part 2 of this video lecture. We are going to talk now about chapter 6, which is all about alkyl halides, alcohols, amines, ethers, and various sulfur-containing compounds. And it sounds like a big, long list of things to cover, but in reality this is more of an introductory chapter. Some of it you've already seen. You've already seen alkyl halides, for example. We'll talk about a few more details of alkyl halides, including an important reaction that they undergo to form organometallics. Alcohols is just going to be an introduction. Likewise with amines, ethers, and thio or sulfur-containing compounds, it's just going to be an introduction. We're not going into great detail here. As chapters go, this one's not terribly difficult, but there are some homework problems at the end of this chapter which you definitely want to work on before Friday's exam, so I strongly encourage you to do that. Here we go. We're going to start with the alkyl halides. What I want you to remember is that you've seen alkyl halides before. Alkyl halides are any sort of alkane molecule that we've drawn with a halogen on board. So this one happens to be 1-chlorobutane. You knew that already. One thing I didn't emphasize when we introduced alkyl halides last time, and it actually showed up in some homework problems which were covered in an earlier chapter, and it's time now to go back and make sure we examine it, is this notion of polar covalent bonds. You know, the halogens are kind of special because they're so electronegative. When you put a halogen like a chlorine or a fluorine or a bromine or an iodine on a carbon atom, the electronegative nature of the halogen pulls electron density towards it. And what I'm drawing right here is what's known as a bond dipole moment. It's a vector arrow, similar to the sort of vector arrows you might draw if you took a physics class, which shows direction and magnitude. The direction is just the direction pointed by the arrow, and the magnitude is related to the size of the arrow I draw. So with a larger arrow, it implies a larger bond dipole moment. What is this bond dipole moment? It simply means the following. These two electrons of this carbon-chlorine bond are not shared equally. The chlorine, being more electronegative, is going to pull more of that electron density towards it. That gives the chlorine extra electron density and a delta negative charge. That little delta sign means slight, so a slight negative charge. This is not a formal charge. This is a slight negative charge as a result of the difference in electronegativity between these two atoms. Likewise, the carbon loses out. It doesn't own equally one of the electrons of that two-electron covalent bond. Chlorine grabs part of that electron density, and the carbon has a slight positive character. This is known as a bond dipole moment. What's important about it, from our perspective, is that this carbon atom now has got a little bit of positive character, which makes it electrophilic. And we've talked about nucleophilic and electrophilic atoms before. This carbon is electrophilic. Electrophilic because it's attached to an electronegative chlorine, which pulls electron density out of that two-electron bond, making this carbon deficient in electrons. And so now it desires electrons because it's got a partial positive charge. Well, you've seen lots and lots of examples of alkyl halides before. This is just another example. But let's think about it in a slightly different way. One of the problems you did before was to draw all the constitutional isomers associated with various formulas. If we think of a butane is a C4H10 structure. The corresponding structure of this alkyl halide, in which there's one chlorine, must have one less hydrogen. We've essentially taken a hydrogen away, and in its place we've put a chlorine. So the formula for an alkyl halide should be similar to the formula for an alkane, where the total number of hydrogens and halogens adds up to, in this case, 10, 2n plus 2. This is C to the n, H to the 2n plus 2. Now the total number of hydrogens and halogens should be 2n plus 2, where n equals 4. And if I asked you to draw all the isomers, not just constitutional isomers, because now we know about stereoisomers, but all the isomers total that have the formula C4H9Cl, well, we would go about it in the same way. We would start with the longest chain of carbon atoms, continuous carbon atoms being 4, and we would put our chlorine there to begin with. Then we would move our chlorine there, but now when we do that, we realize that actually occurs in 2 ways. These are chiral compounds, and I've now drawn the pair of enantiomers that is 2-chlorobutane. So we can put our chlorine at carbon 1 or at carbon 2. When we put it at carbon 2, we actually get a pair of enantiomers. What else could we do? I think we've exhausted the possibilities where 4 carbons is the longest continuous chain, so we could now move to 3 carbons as the longest continuous chain. Then we have to add a 4th carbon and a chlorine. We could also add the chlorine at one of these positions when we have that same arrangement of carbon atoms. Neither of these carbons is a stereogenic center, nor is that carbon. None of them is chiral. And so the only 2 chiral compounds are those 2 right here. We would call this one 1-chlorobutane. This one right here is the R absolute configuration. This one right here is the S absolute configuration. So we would refer to this one as R2-chlorobutane. I can barely squeeze it in there. And this one would be the corresponding S2-chlorobutane. Over here, I would start numbering 1, 2, 3 in order to give my total set of substituents the lowest possible number. So this becomes 1-chloro, 2-methyl-propane, and 1, 2, 3, 2-chloro, 2-methyl-propane. So those are all my isomers that are C4H9Cl. So the way I would go about finding all the isomers in which a halogen atom happens to be present is pretty much exactly the same as what we've already seen in the past. All right, so you've seen various types of alkanes and cycloalkanes. The fact that we throw a halogen on board doesn't really make much of a difference, except now we appreciate that the halogen, being electronegative, is going to pull electron density through that sigma bond toward the halogen atom, making it delta negative, and the corresponding positive or delta positive charged carbon is attached. That makes the carbon electrophilic. Can't emphasize enough how important that point is. On Friday, when we come back and we have a lecture in person, we're going to be talking about a new chapter and the electrophilic nature of alkyl halides, and in particular the carbons that are attached to the halogen, is going to become a very important part of the discussion. Now, when we take compounds like this one, which I will redraw without all the extra stuff. By the way, there's no stereogenic center there because this path is exactly the same as that path. I'm showing the bromine coming out of the plane of the board. That is exactly equal to this molecule. Just take this one and flip it over like a pancake, and now you've got that one. They superimpose. They're exactly the same. This is a cyclohexane. I could be drawing this in a chair form, I suppose. Be just as nice, nothing wrong with it. But there's nothing wrong with drawing two-dimensional cyclohexanes as well, as long as that's appropriate, and in this case it is. What I want to tell you is that there is an important class of molecules called organometallics, which can be derived from alkyl halides. For example, if I take this particular bromocyclohexane and I treat it with a metal, but not just any metal, magnesium. Notice this little naught right here, this 0 or naught. That implies that I'm dealing with metallic magnesium, not magnesium cation. Metals are typically seen as cations, like sodium chloride. The sodium is sodium Na+. Or magnesium chloride, you've got MgCl2, Mg2+. So metals, we're used to seeing them in salts where they're cationic, but I'm talking about the bare metal here. If I treat this organometallic with the bare metal, and here's an important thing, this reaction has to be run in a very special solvent, in ether. And ether, as it turns out, is one of the topics of this chapter, so I'm going to tell you more about ethers in just a few minutes. But that's going to be a solvent. It's going to be an important solvent, and this particular reaction requires this particular solvent, an ether for a solvent. If you don't have an ether for a solvent, the reaction doesn't work, and therefore we've got to show the solvent either above or below the arrow. Notice that I put my magnesium metal above the arrow and the ether below the arrow. It makes no difference how you show it as long as they're near the arrow, so I know this is my reactant. These are the reagents and the solvent that are required. You can convert an alkyl halide into the corresponding organometallic, which looks like this. Look what happened. The magnesium essentially inserted between the carbon and the bromine bond, and now it is a carbon magnesium bromide. This particular type of reagent is known as a Grignard reagent, and it is a very special type of organometallic. What's so interesting is that we have just completely changed the electronics around the carbon atom. For example, here, as we've been discussing, there's a bond dipole moment from the less electronegative carbon to the more electronegative bromine, meaning the bromine is delta minus and the carbon is delta plus. But once we produce an organometallic, look at, now the carbon is bound to a metal. And metals are actually electropositive. What that means is that between these two atoms, carbon and the metal, the carbon is the much more electronegative atom. So now the bond dipole moment reverses. Carbon is now delta negative, and the metal is delta positive, as metals like to be, positively charged. Very interesting. The carbon here, where we started, was electrophilic. Being deficient in electron density, it desires electrons. It's electrophilic. But now, once we make an organometallic, this Grignard reagent, it's actually the opposite. It's nucleophilic, meaning it desires a positive charge. Very, very interesting. We've changed the electronics around the carbon atom. In addition to producing a Grignard reagent, you can also take an alkyl halide and produce an organolithium by combining it with lithium metal. Technically, it requires 2 equivalents of lithium metal. The solvent is a little less particular here. You can use quite a few different solvents, and so we're not going to necessarily list the solvent here. In fact, most of the time, in most organic reactions, we're not going to list the solvent. This first one you learned here, this organometallic reaction leading to a Grignard reagent, does require ether as a solvent. You have to show it every time. But here we don't need to show the solvent because it can be several different things. In the case of an organolithium, we just simply produce the corresponding organolithium where the carbon is directly attached to lithium. The bromide is long gone. In fact, the bromide falls off and coordinates with another lithium to give you a lithium bromide. That's why we require 2 equivalents of lithium. This is not an essential part of the story. This lithium bromide is a byproduct, and most of the time I'll just ignore it. The essential part of the story is this one right here. This is the so-called organolithium. And just like the Grignard reagent, that's a metal attached to a carbon, so now the bond dipole moment is in this direction. The electropositive metal is pushing electron density onto this electronegative carbon, making the carbon delta negative and the metal delta positive. Once again, we've got a nucleophilic carbon in this organometallic. So what we've seen is that we can form 2 different types of organometallics: Grignard reagents and organolithiums. Grignard reagents and organolithiums, we can produce them from any alkyl halide. This one happens to be that R2-chlorobutane that I had before, I believe. And how would I do it? Well, to make the Grignard reagent, I would use magnesium metal, Mg0, with ether. Got to show the ether here. And that would give me the corresponding Grignard reagent. Or I could treat it with lithium metal, solvent's less important here, to produce the corresponding organolithium. Now notice that in this particular case, I'm not showing the stereochemistry, even though I'm starting with a particular stereochemistry here. I'm not showing it, and that's because the stereochemistry is not always maintained when you produce these organometallics. Sometimes it's maintained a little bit better than in other instances, but it's not always well maintained, and so we're going to account for the fact that you might actually have both stereoisomers present here. That's fine. So when I draw a bond like this, which is not a wedge bond and is not a dashed line, that really means that it could be either. In other words, you could have either stereoisomer, either enantiomer present. Well, these organometallics are very, very interesting species, and one of the things you need to know about them is that they are very strong bases. In fact, they're exceptionally strong bases, which means you have to keep everything that's even mildly acidic away from them. And that includes water. Water is a big no-no when you're making organometallics, because the organometallics will just immediately react with the water. We don't think of water as being a very acidic compound, and compared to things like sulfuric acid, it's certainly not. But it is plenty acidic for these terribly strong bases. The stronger the base, the weaker the acid you need in order to have an acid-base reaction. What's going to happen is that if you have an organometallic, much like the one I just showed, in the presence of water, these two electrons right here of this carbon-magnesium bond, the ones that mostly belong to the carbon atom because of this bond dipole moment. In fact, let's just digress for a second. We can show a resonance form in which we place both of those electrons on carbon. Look at that 2-electron arrow. This now looks like an ionic bond rather than a polar covalent bond, and it is acceptable in this case. Clearly this is the better resonance form, but this is a reasonable resonance form because the metal is so electropositive. And so this lone pair of negative charge, that's the same as that polar covalent bond right there. These are just two different resonance forms. We're showing it in two different ways. We can take these electrons and pick up this acidic proton very, very easily. Now notice that there was already one bond to hydrogen, and so there's still that bond to hydrogen, but I've just picked up a new bond to this proton. Look at this proton. Those two electrons go to the oxygen. This hydrogen was delivered to the carbon as an H+. This is truly an acid, which is protonating my strong base. What's left over as a byproduct is OH- as well as MgCl+. That's just going to be an inorganic salt, not an essential part of the story. The essential part of the story is this alkane. Now, this is a reaction you would probably like to avoid. Alkanes are kind of boring compared to alkyl halides. We already had a halogen on board. If you forgot where this came from something like this chlorine, which was treated with magnesium metal in the presence of ether. So somehow we started with a 2-chlorobutane, which I believe was this particular stereoisomer when we started, although it could have started with the other stereoisomer, produced this organometallic, and now we've just protonated it and gone back to a boring alkane. So this is, generally speaking, not a very desirable reaction. And when you make organometallics in the lab, you work very, very hard to make sure that there's no water around. You dry your glassware very, very carefully using a torch, or you put them in a high temperature oven for an extended period of time to completely dry the glassware. When you run the reaction, you have all sorts of extra precautions set up so that water does not re-enter. There's a lot of water in the atmosphere, in the air, particularly in the summer when it's humid, but even during the winter. There's moisture in the air. You got to keep all that water away, and we have special tricks to do that. They're really not all that tricky or all that difficult. We use things like drying tubes and other things. Keep the water out. However, it does turn out that if you prepare an organometallic, I'm going to make the organolithium this time. So technically I need 2 equivalents of lithium because I'm also going to produce lithium bromide, which again is a byproduct and I don't really care about it. And I let that react not with water but with D2O, deuterated water. This is interesting. Deuterium is an isotope of hydrogen, and we don't have a lot of ways to introduce deuterium into organic compounds in a controlled fashion, but this is one of them. D2O behaves just like H2O. In other words, we can take our very basic electrons. Now I'm not showing them as a lone pair, but I'm just showing them as polar covalent bonded electrons. I'm still going to take both of them and grab a deuteron, which is like an H+, only it's a D+. These 2 electrons kick onto the oxygen, and the result is that I now have added a deuterium. There was already 1 bond of hydrogen there, which wasn't shown, but now it is. And so I have selectively placed 1 deuterium atom onto this cyclohexane. And this is a very creative and clever way to do it. Normally we avoid water, but if we're trying to introduce deuterium, we might intentionally add D2O. And we can place 1 deuterium exactly where the organometallic bond was. And if we're keeping track of byproducts, there would also be OD- and lithium plus. But again, that's inorganic byproducts, not an essential part of the story. So this is kind of your first synthesis. If I told you, for example, you can start with anything you want, any alkyl halide you want, and show me how you would prepare the following compound. This looks like butane, except one of the hydrogens on this terminal methyl group here has been replaced by a deuterium. You were told you could start with any alkyl halide, so let's start with a chloride in which the chlorine is at the same place that we want the deuterium. Let's go ahead and make an organometallic. We can make 2 different ones. We can either make the Grignard reagent or the organolithium. And then let's take either of them, it doesn't matter which one, and treat it with D2O, and that will place your deuterium exactly where you want it. So organometallics can be utilized to make deuterated organic compounds. Although it's going to turn out there's a lot of other uses for organometallics, and we will study those later on, particularly in organic chemistry too. Well, that takes care of alkyl halides. Let's now move to alcohols. Alcohols are very simple. They're just compounds that contain an OH group. So frequently you'll see me do something like this. I'll write R. This R just means something organic. Attached to an OH group, that defines an alcohol. So some organic moiety attached to an OH group, that's an alcohol. It could be as simple as a methyl group attached to an OH group, that is methanol. It could be an ethyl group attached to an OH group, that is ethanol. It could be a 3-carbon propyl system attached to an OH group. It turns out I can do that in 2 different ways. I can have 1 propanol or 2 propanol. This 2-propanol is often referred to as isopropanol. In fact, you can go to the drugstore and buy isopropanol in a bottle. Notice how these things are named. Let's go back to methanol. We take the base alkane, methane, we subtract the E ending, and we add all. Base alkane minus E plus all. So methane minus E becomes methan plus all, methanol. Ethane minus E, ethanol. 1 propanol, 2 propanol. Naming alcohols is pretty straightforward and pretty simple. And it extends to ring compounds as well. So if I had a 5-membered ring with an alcohol on it, it would be cyclopropane minus the E, cyclopropanol. Cyclopropanol. It's very, very simple. What if we had a long molecule like this, and we have an OH group there, and a bromine here? So now we have an alcohol and a halide all in the same compound. It's no big deal. We can name this thing. The one thing you need to know, though, is that the alcohol group takes priority over halides and other alkyl groups. So, for example, for numbering purposes, you want to make sure you give the alcohol the lowest possible number compared to halides or alkyl groups. So we have to number in this fashion right here. In fact, just to re-emphasize this point, maybe it would be better to even add another halogen out there. So now as you look at this, 1, 2, 3, 4, 5, we're not going to start numbering here at carbon 1, even though that would give me a lower set of positional numbers for all the substituents, because the alcohol takes precedence. I have to give the alcohol the lowest possible positional number, which would be 2 instead of 4 if I'd gone in this direction. Okay, now you might also notice that there's a couple of stereogenic centers here. So this one is S, and this one is, see, working out atom by atom, carbon, oxygen versus carbon. The oxygen wins, even though chlorine's heavier than oxygen, we don't get there. So we're going to go here to here to here. This is a counterclockwise direction, but the group of lowest priority is in the front, so that's going to become R. So this becomes a 2S, 3R, and now we got to put our substituents. There's no stereogenic center out there, but I still have to include the chlorine substituent. I've got a bromo and a chloro, so it's going to be B before C, 3 bromo, 5 chloro, and this is a 5-carbon alkane, a pentanol, and since it's at, the alcohol is at carbon 2, 2 pentanol. So that would be the full name. 2S, 3R, 3 bromo, 5 chloro, 2 pentanol. So this is really just an extension of the sort of naming we've already done. The only thing that's different is that the alcohol is named as an alcohol, of course. The last thing I want to say about alcohols is that there are also these things called diols. And sometimes we refer to diols as glycols. Glycol is actually an older term. It dates back quite a few years. People used to refer to diols as glycols all the time. Diols are just compounds that have 2 OH groups. So you could just call this 1,2 ethane diol. Notice that with diols we do keep the E of the alkane and we just add diol. 1,2 ethane diol. But the truth of the matter is, this is more commonly referred to as ethylene glycol. That is a historic name, a trivial name which predates IUPAC nomenclature. It doesn't even make sense, to be honest. The name ethylene implies an alkene, and there's no alkene here. Glycol makes sense. That means 2 alcohols. But it doesn't really tell us that they're 1, 2 with respect to each other. Anyway, ethylene glycol is a very important name because it's commonly used still today, despite the fact that it's not a proper IUPAC name. And another diol, there are lots of examples of them, would be this one. We would name this 1,3 propane diol. Again, it's kind of tricky because when you have diols, you leave the E in there and you just call it propane diol. 1,3 because 1, 2, 3, the 2 alcohols in this particular case are located at carbons 1 and 3. This is also known as propylene glycol. Again, propylene doesn't make a whole lot of sense for this structure, but it's a historic name. Now, what you should know about diols or glycols is that there are these 2 alcohols functions present somewhere in the molecule. You should also know something about these particular 2 glycols or diols. If you own a car, you might have antifreeze in your car. The antifreeze circulates around and makes sure that your engine doesn't freeze up in the winter and doesn't overheat in the summer. So it plays a very important role in terms of regulating the temperature of your car engine so things don't go haywire on you. Years ago, if you bought antifreeze, a real common antifreeze was Prestone antifreeze and others. They were made of ethylene glycol, this stuff right here. This is a very good antifreeze because it's got a higher boiling point than water and a lower freezing point than water, so it keeps everything cooler, doesn't freeze up, doesn't boil on you. But it turned out that ethylene glycol was toxic to animals, and so if you had an old car which was leaking some of your coolant, your ethylene glycol, your Prestone, whatever the case may be, and your dog came around and started licking it up, the dog would be poisoned and might very well die. And apparently it's a sweet tasting compound, at least to dogs, so they liked to lick it up. So that was a real bad problem. This propylene glycol is a replacement. It serves the same function, but it turns out it's not toxic to animals. And so if there are leaks, you don't have those same issues. So where antifreeze is concerned for your car, those are two very important compounds. Let's move on now to talk a little bit about amines. Amines are organic compounds in which we have an NH2 or amino group attached to the organic arm. These would be so-called primary amines because the nitrogen is attached to only one other carbon. It turns out it's also possible to have a secondary amine and even a tertiary amine. Notice that in the primary, secondary, and tertiary amines, the nitrogen has 3 sigma bonds, 2 to hydrogen here and 1 to an organic group, plus a lone pair. 3 bonds, lone pair, 3 bonds, lone pair. Nitrogen should have 5 electrons in its valence shell to be neutral, and in all of these cases it does. 1 from each of the covalent bonds, that makes 3, plus a 4th and a 5th from the lone pair. So the amines all look the same in that regard. Now, it's also possible, and we'll see how in just a few minutes, that you can have a nitrogen which is simultaneously bound to 4 different things. I happen to make all 4 R groups, but they could be some combinations of hydrogens and R groups. In this particular case, there's no more lone pair, but there is a positive charge, and we refer to this as an ammonium ion. So you have primary amines, secondary amines, tertiary amines, and ammonium ions. Those are all related to this discussion of amines. Let's talk about how to name amines. Turns out you have a couple of options. What you can do is you can name them similar to the way we named alcohols. So for example, this has got an amino group here at carbon 1 of a butyl system. We could take the base alkane, which would be butane, subtract the E, and add amine. So instead of butanol, which was what we would call this if there was an OH group there, it's butanamine or butanamine. Since it's at carbon 1, we would call it 1-butanamine. So you can name it much the same way we name alcohols if you prefer, but there's also another way. You could also just refer to the amine group as a substituent and call it a 1-amino, that would be the substituent, butane. So with amines, we actually have options. You can name them in a couple of different ways. Both are accepted by IUPAC. Let's look at this one. This one's a little trickier. Here I have a secondary amine. Notice that this was a primary amine up here. Now I've got a secondary amine. If I were going to name it kind of like I did here, 1-butanamine, well, the carbon chain that's the longest right here is this propyl group. It would be a propanamine, a 1-propanamine, but that doesn't account for this methyl group out here. I need to account for that as well. I'm going to treat this methyl group as though it's a substituent. But if I number the longest chain, the methyl group's not part of that numbering system. I don't say it's a 1-methyl anything. Looks like I'm about to run out of battery. So I'm going to have to stop here after I name this, and then we'll move on in just a second with a separate video to wrap this up. We're almost done. The way I'm going to handle this is this methyl group is on a nitrogen, so I'm going to call it an N-methyl. N-methyl 1-propanamine. N-methyl means the methyl group is on nitrogen. That's what the N means. I don't give it a number. I give it an N for methyl 1-propanamine. And likewise, what if I had something like this, a tertiary amine? These are both methyls. I would call it N, N dimethyl 1-propanamine. Notice that just like before when we talked about numbers, every substituent has to have a number. Well, here, these two methyl groups are treated as substituents on a nitrogen. They don't get numbers, but they both get an N. So it's NN dimethyl 1-propanamine, not just N dimethyl 1-propanamine. Well, I can see that I'm about to run out of battery, so I'm going to have to fix that situation and start this over again to finish up the chapter. There's only a couple more minutes to go, but it's going to have to be on a separate video.